Welcome. Today's webinar is Electric Bus Deployment, Cost and Environmental Equity. My name is Brendan Williams. I'm the Research Program Administrator at Portland State University's Transportation Research and Education Center. TREC leads the National Institute for Transportation Communities, a university transportation center funded by the U.S. Department of Transportation. NITC consortium members are the University of Utah, University of Oregon, University of Arizona, University of Texas at Arlington, and Oregon Institute of Technology. NITC's research priority is improving mobility of people and goods to build strong communities. Our presenter today is Dr. Cathy Liu. She is an associate professor in civil and environmental engineering at the University of Utah. Her background is in data-driven applications in transportation and multimodal transportation network modeling. She has conducted research to assess the efficiency of transportation networks and the impact of emerging technologies, such as shared mobility, vehicle electrification, and automation. Our next NITC webinar is on July 13th at 10 to 11 a.m. Pacific time. Diana Mason from the University of Oregon will present on the impact of ride-hail services on the accessibility of nonprofit services. Okay, so today's webinar will be about the presentation by Cathy will be about 40 minutes long. Then we'll have 15 minutes to answer your questions. During the presentation, please put your questions in the Q&A box. And then we will get to them at the end. We just have one presenter, but we'll try and take them in order. And if you have a specific question about a slide, or I know Cathy is showing us an online tool today, we'll try and go back to those to bring them up. After the webinar, you're going to receive an email with a link to the video recording and presentation slides. This webinar is eligible for 1 hour of continuing education credit. Instructions on how to redeem the credit will be included in your post-webinar email. So with that, I'm going to turn it over to Cathy.
Thanks, Brendan, for the introduction. I'll share my screen right now. So I hope everybody can see my screen right now.
Looks good. Thanks, Cathy.
Yeah. Sounds good. Cool. So I'll get started. So first of all, thank you very much for everybody for your time to attend this webinar. So today's presentation is about electrical bus deployment framework for improved air quality and transit operation efficiency. So of course, battery electric vehicle is receiving an increasing amount of attention from transit vehicle industry and also from transit agencies because of a couple of different perks, right? So because of the recent advancements in battery technology and also the zero emission low maintenance cost perks. So today's presentation, as Brendan mentioned, is based on a project that we have recently completed with NITC to actually evaluate the deployment of electric bus. My name is Cathy Liu. As Brendan mentioned, I'm an associate professor at the University of Utah. I do a lot of multimodal transportation modeling, performance assessment. In recent years, I'm particularly interested in how some of the emerging technologies and shared mobilities could affect the multimodal transportation network in general. Before I start or go into the technical detail for this presentation, I do want to give a very short project briefing. We are very grateful, again, for NITC's support on this very timely and intriguing topic. So this is This presentation is based on NITC project number 1222, and then it is a multi-institutional collaboration across 3 different campuses. Of course, University of Utah, which is my home institute. We also have Dr. Aaron Galoob from Portland State University and Dr. Ran Wei from University of California, Riverside as the co-PM this project. I also have my graduate student, Yirong Zhou, who I believe is with us today in this webinar. He has been the technical lead implementing all this modeling work and all these results. So hopefully at the end, he has a chance to interact with the audience. So the project itself is actually grounded on a history of research efforts that my lab have spent on in terms of the public transit electrification. So several years ago, our local transit agency, Utah Transit Authority, UTA, received this federal FTA grant on low or no emission grants to purchase zero emission transit vehicles to reduce the environmental footprint of public transit. So all the effort actually was motivated and initiated from that point where our region really want to prioritize the need to support this transition of transit fleet to these energy efficient transit vehicles. So my presentation throughout today's webinar can be broken down into 4 different parts. I'll talk a little bit about the introduction, providing a little bit background in terms of electric public transit. I'll talk about some of the preliminary effort or previous effort that we have developed in terms of building optimization framework on how to deploy the electric vehicle spatially and temporally. And then I'll particularly talk about this NITC project and some of the highlights that distinguish this effort from our previous effort. And then lastly, this NITC project, we also build an online visualization system to allow users to interactively explore our results. So I will briefly talk about that as well. So first of all, I'll go into the introduction. So battery electric buses, I will refer it as BEB from this point on. So BEB is usually driven by an electric motor and then gets energy from the onboard batteries. So as a lot of people already know, it has a lot of perks with zero emission, low maintenance cost, and low noise pollution. So NREL, the National Renewable Energy Lab, they conducted a research a couple of years ago, and then they concluded that BEB actually is nearly 4 times more fuel efficient compared with the traditional CNG buses. But purchasing the BEB actually requires some of the associated charging infrastructures to keep the bus moving. So there are essentially a couple of different types of charging infrastructures, really depending on the needs of the transit agency, and then depending on some of the fleet parking space requirement. So there's en route charging, where the bus can use a roof-mounted pentagram, and then there's the in-depot charging, where it's usually placed in the bus garage, so the bus can be plugged in to get charged. So there are a couple of different challenges in terms of deploying the BEB or integrating it into the current public transit system. That's also distinguishing the electrical transit versus the electrical vehicles, because transit system have some unique spatial temporal characteristics. So first of all, to support this long daily operating time and then high daily mileage, so some of the BEBs will need periodical en route charging at bus terminals, and of course overnight charging at bus garages. So when we deploy the BEB, it's not only about replacing the buses, but also we need to determine where to deploy these en route charging stations and overnight depot charging stations. And then the second of all, so when we deploy these BEBs into the current transit operations, we want to make sure that it fit or align with the transit routes and schedule as much as possible so that we can enable smooth transition from the traditional CNG buses to the BEB. So the concern for potential interference with the current operation routes and schedule could really impede the acquisition of BEBs. But on top of that, we also want to make sure that the deployment actually benefit the most to those people that are in need. This is especially important problem for Salt Lake City because the greater Salt Lake region is actually considered the non-attainment area for PM 2.5 by EPA. So it will be very important for us to deploy the battery electric bus or the BEBs so that the area with the highest pollutant or the people who are exposed to the highest pollutions can actually be benefiting the most. So a couple of things that we want to consider when we actually deploy this system. First of all is when any agencies decided to replace their current CNG buses with electrical buses, they probably do not really have all the budget to replace all this bus fleet one at a time. So when we come up with the deployment framework, we really want it to be a phased approach so that the transit agencies have the flexibility and freedom to actually choose which particular plan they want to implement it within the short term, mid-term, or the long term. And then, of course, as I mentioned, we really want this to benefit the disadvantaged population because oftentimes they are the vulnerable type of people who are very transit dependent and then very vulnerable to air pollutions. So when we deploy these BEBs, we want to make sure that those people are considered and then the area that they usually perform activities are actually receiving the priority. So this kind of elicits some of the objectives that we try to achieve throughout the series of work that we have already done. So the two objectives that we really want to achieve in terms of the battery electric vehicle or BEB deployment, first of all, is we want to deploy a spatial temporal analytic framework to assist agencies in identifying the optimum deployment of BEB system. By system, I mean, it's not only which buses to replace, but also where to construct the charging infrastructure to accommodate the BEB's need. So each transit agency will have different priorities, would have different concerns and objectives. So it could be to minimize the cost to reaching the maximum amount of people or ridership. So how to reconcile or how to consider all these different competing goals will be some of the issues that we want to address. And then second of all, as I actually just a little bit mentioned earlier, is how do we optimize this BEB deployment considering multiple different goals? So maybe not only cost, but also some other priorities like environmental equity that we are trying to address in this particular study. So in the next session, I want to talk about some of the previous effort that we have done, which leads to this NITC project that we recently completed. So several years ago, when we started on this electric bus deployment, we did our first attempt to develop this spatial temporal analytic framework to identify the optimum deployment of the BEB system. So back then, upon discussion with the UTA, because that was the project sponsored by UTA, back then, we were really interested in how do we deploy this BEB system, trying to achieve the minimum cost, because at the beginning of a grant project, probably this is one of the biggest concerns that everyone is interested in. So back then, when we developed this framework, the ultimate objective was to minimize the cost. So as you can see, when we construct this optimization model, it's really trying to minimize the cost of 3 different components. So this part, ZI, represent the number of electrical buses. So this is the total cost of the electrical bus. And then YJ and YG represent the cost of on-route charging and the in-depot charging. So this looks like a very simple objective function, but actually associated with that, we actually developed about 15 different constraints to make sure all these spatial temporal features of the transit system are actually incorporated. So in this particular model, we run through this optimization model and get the solution for each and every scenario. Essentially, UTA or any transit agency actually, they input the number of buses they want to replace with BEB. And then running through this optimization model based on a lot of constraints that we set up, we'll be able to produce the output of which exact buses that the agencies want to replace, and then what are the location and the numbers of both in-depot charging and on-route charging stations in a goal to minimize the total cost. So we actually presented this seemingly complex model in one of the journal papers that we have published. So I don't want to go into detail about how some of the constraints are actually set up, but if any of the audiences are interested, feel free to go to this journal paper that we published back in 2018 to take a look at the algorithm, how some of the parameters and constraints are set up. But I want to use this particular slide to show just a snippet of how some of the spatial temporal features of the transit system are actually considered. So the graph here on the right side essentially is an elevated graph for a transit vehicle traversal throughout a sequence of terminals during the day. So you can see that there is a transit vehicle that depart terminal J3 at time T1, and then arrive at J1 at time T2, go back to J3 at time T3, and then finally switch to another route and arriving at terminal J2 at time T4. So one of the decision variables in our constraint is actually this cumulative mileage for any bus at any terminal. So it has to be less than the driving range for the BEB. And then if the BEB gets charged, then this cumulative mileage variable is gonna be reset to 0. And then the temporal aspect, when we consider this optimization constraint, is to ensure that if there are multiple buses arriving at a particular time, at a particular terminal at the same time, we need to make sure that there are enough on-route charging stations at that place so that it can satisfy simultaneous charging need for all the BEBs arriving at that particular terminal. So this is just a very simple example to show you how some of the spatial temporal features are actually included or considered in this optimization. So the framework that we developed back in 2018 essentially is used to examine the potential adoptions of the BEB system into the bus fleet operated by our transit agency, UTA. So UTA is the primary transit provider throughout the Wasatch Front of Utah. So back then, when we tried to evaluate that framework, we actually used a specific model that UTA referenced us to. So this particular model is for Potera Transit Fleet FC Plus, so fast charging plus. So the nominal range for that particular model is 62 miles. And then the associated charging infrastructure where we get data reference that the on-route fast charging is taking about 10 to 13 minutes and then can charge 6 fleets simultaneously. And then the in-depot charging will be placed in the bus garage so that all the buses can be charged overnight. So each in-depot charging can charge 12 different FC Plus simultaneously. So for UTA's network in particular, the buses that we run this optimization model from, we have a total of 467 diesel or CNG buses. So these buses actually serve 112 fixed and flexible bus route on a typical weekday. So this is the data that we got from UTA and then as the input into our model. So among this 467 buses that we try to evaluate the feasibility to be replaced with BEB, about 135 of them will not be able to get charged before running out of the battery if they were to be replaced. So we actually eliminated those from our data pool. So this actually leaves about 332 potential replacement to evaluate our optimization. And in terms of the cost for each and every bus and each and every charging infrastructure, so back then, the cost quote for FC Plus is about 750,000. An on-route charging station is about $500,000, and then an in-depot charging station is about 50,000. So later on, when I present the NITC work, you will see these numbers are a little bit different because we have a new set of data that we reference to later on. So having all this data that we got, we actually can pre-screen the eligible or potential sites for on-route charging station. So the criteria has been quite simple at this pre-screening stage because we assume that a BEB can only be getting charged at the terminal if there is a bus dwell at that terminal for more than 10 minutes. Because it requires at least 10 minutes for the vehicle to get charged by the on-route charging station. So this leaves us about 70 potential sites for the on-route charging station. So these sites are actually highlighted on the right side of this figure. After running our model, you can see that on this graph that I'm showing here is actually the results based on running our optimization through every single scenario. So each scenario actually represents a different number of buses that the agency would like to be replaced. So starting from one bus to be replaced all the way to that 332 buses that will be replaced. So this figure essentially shows the cost breaking down into each different components in terms of the cost for the transit fleet, the cost for the on-route charging station, and the cost for the in-depot charging station. Of course, the blue line represents the total cost. So you can see that we didn't assume any discount associated with the size of the order. So there will be a strict linear relationship in terms of the number of adopted BEB versus the cost for the BEBs. And then as you can see that before, I hope this is a little bit distinguishable. So before 111 buses, somewhere in here, the blue line and the green line actually align perfectly with each other. A little bit, excluding the on-route chargings, in-depot charging stations. So that is because for the first 111 buses that were to be replaced with BEB, there's no need to install any on-route charging stations because their daily range is less than 62 miles in total. So there is no need to install any of the on-route charging stations, and that cost is not needed at all. But as you can see that as more and more buses are to be replaced with BEB, the total cost is actually going to be increasing a little bit scale up towards the higher end. So that is because the increase of on-route charging stations. Okay. So given that there are about 332 existing buses feasible for replacement, so actually 221 of them will need this on-route charging if they were to be replaced with 221, if they were to be replaced with the BEVs. So among these 221 buses, so actually our model will be able to produce the maximum number of BEVs that can be served by each possible number of en-route charging stations. So you can see that on this particular graph, it shows the number of en-route charging stations with the number of BEVs that they are able to serve. Actually, the first en-route charging station can serve up to 45 BEVs. So later on, when I show the specific application, you will see what I mean. And then eventually, if we were to replace all this fleet, 332 vehicles completely with BEVs, then we will only need 36 en-route charging stations in total. Okay. So this is just kind of a trade-off, a curve showing the number of BEVs that can be served by the number of en-route charging stations within the network. So I want to run through a couple of examples or example cases of the results that our optimization model produced, and kind of give the audience a flavor of how this model can be used by transit agencies to guide some of their deployment, BEV deployment planning. So this is the first case that I want to present. So this case represents the case where we deploy 111 BEVs onto the network. So it shows out which routes that this bus will be traveling on. And then, yeah, so that's pretty much it. Serve the route, the space, the routes and the space-time trajectory. So you can see that with this 111 BEVs, they do not require any of en-route charging stations because their daily range is less than the BEV's range, less than 62 miles. So the daily mileage for all these 111 BEVs is ranging from 10 to 60 miles. And then these BEVs are serving about 51 different bus routes. And then the figure on the right basically shows the elevated temporal figure to show the origin and destination of all this route. So some of the vehicles actually are taking long distance route once or twice a day, and then there are also some of the fleets that are taking a shorter route but multiple times a day. So this is another scenario where we only set one charging station, one en-route charging station, and actually this en-route charging station will be able to serve up to 45 BEVs. So this one, you can see that the charging station is actually sited in the Salt Lake Central Station. So this is actually what we call intermodal hub in Salt Lake City that accommodate a couple of different multimodal transportation systems, not only the regular buses, but also the commuter rail, front runner, and also the light rail. So this is also building upon this particular results. UTA is actually building a charging garage to accommodate all these charging needs for our future electrification of the public transit system here. So you can see that just by citing one en-route charging stations, it will be able to serve about 45 different BEVs within the region. And then with this elevated temporal graph, you will see that the origin and destination for different routes served by these different BEVs across different time of day, from 6:30 a.m. to almost 10 p.m. So the daily range for this 45 additional BEVs are ranging from 88 miles to 252 miles. Okay, and then further along, this is another example where we continuously increasing the number of BEVs to be deployed. And then this is the case where we have 5 en-route charging stations built. And then where should we build it? So these 5 en-route charging stations are actually built, one again in the Salt Lake Central Station, and then there is one in Salt Lake City downtown area, and then one in Ogden area, one in Lehigh, and one in Mill Creek. So you can see that these 5 on-route charging stations will be able to serve an additional 103 newly adopted BEVs. So these BEVs will have a daily mileage of 88 miles all the way to 372 miles with 29 additional bus routes that are served. So the last scenario that I want to show here, just as a case example, will be if we were to replace all this transit fleet within the network. So recall that at the very beginning, we mentioned all this transit fleet that are eligible for replacement totals about 332. So if we were to replace the 332 buses with the BEV, so how many charging stations do we need? So a total of 36 charging stations, on-route charging stations, will be sited throughout the entire metropolitan area. And then you can see that the daily mileage that this bus serves actually increased significantly all the way to 456 miles, with an additional of 67 additional bus routes that's served. So this is some of our previous effort that my team actually have completed, and actually build upon this. We further advanced our optimization model, which leads to this NITC project. So for any transit agencies, of course, at the beginning, cost has always been a dominant focus when optimizing the development, the deployment. But one of the very important aspects, or one of the very important goals, is also to think about the equity, think about the sustainability of the public transit system, because essentially public transit is to serve the public. So one of the things that we consider for NITC's project is what we call environmental equity. So how do we deploy the BEB system that consider multiple different objectives, not only to minimize the cost, but also to benefit people that are most in need, for example, the environmental equity for disadvantaged population. So our NITC project is basically driven by our motivation to develop this bi-objective optimization, so that we can let people or let user to input different budget limit and then produce an optimum deployment plan. So this slide, as you can see here, is the problem formulation for our optimization model based on the NITC's effort. So instead of, or different from the original effort where we only have one objective, that is to minimize the cost, we actually have two in here. We not only want to minimize the cost, but we also want to maximize the environmental equity. Different from our previous effort, in this one, I'll explain why later. In this NITC project, we will ask user to input a budget threshold. And then by running through our bi-objective function or bi-objective model, again, we will be able to produce the exact buses that were to be replaced with BEB. And then, of course, the number of buses that were to be replaced with BEB, and also the location number of both the in-depot and on-route charging stations. So this work has also been published recently in IEEE Transactional ITS. I won't again explain the detail of the 12 different constraints that we have formulated to consider the spatial temporal characteristic of public transit system, but interested audience, please feel free to refer to our paper for all the technical detail, and I'd be happy to share the paper upon request. But essentially, as you can see on the left side of this slide, we set two different objectives in here. One is called environmental equity, maximizing environmental equity, and then the other one is to minimize the total cost. So by this time, I think by now, probably one of the very critical questions that a lot of people have is actually how do we quantify the environmental equity? So we have researched a lot in terms of the environmental equity, the term, and there are multiple different ways that people have come up with to actually measure this. So there are actually quite a bit of research in terms of the social vulnerability. They actually found out that disadvantaged population often experience high concentration of air pollutants because of the low value of lands and because of the close vicinity to the income earning opportunities. So we really want to come up with a measure to quantify this environmental equity so that we can benefit the disadvantaged population that suffer the most from the air pollution. So the measurement that we come up with is the weighted population. This weighted population is translated into the 2 bullet points that I'm highlighting here. So the population refers to the low-income population, and then the weights represent the PM 2.5 concentration or the pollutant concentration. So essentially, the higher this value is, then probably the more focus that we want to pay attention to for a particular area or for a particular terminal. So by developing this measure to quantify the environmental equity or to maximize the deployment, we really want to make sure that the places where the low-income population that are suffering the most could receive the priority in terms of the environmental benefits that the BEB could bring. So for this particular NITC project, again, we are using the UTA's network. So 467 CNG buses serving 121 routes on a typical weekday, but different from our previous study, we actually are testing a new model because upon the current operation of a couple of electric bus fleet that we have in Salt Lake City, we actually have some operation data that we can refer to. So this particular model that we are considering for this optimization is New Flyers XC40. So this is the model, as I mentioned, that we are currently operating in Salt Lake City. So based on a lot of operational data, we found that the battery essentially is consumed by the motor and also the electric heater. And then during some of the very cold winter weather in Utah, so the electrical heater can actually take up 50% of the battery consumption. So that severely impact the range of this BEB fleet. So the range based on our current data is from 62 miles to 200 miles. So we actually use the safer, the more conservative value, 62 miles as the range for our optimization. And then the on-route charging is set as 10 minutes. So there will be, again, given all these constraints, all these criteria, among these 467 buses, 334 of them will be eligible for the BEB replacement. And when we try to come up with the environmental equity measure, so these are some of the data sources that we retrieved from the local agencies. So first of all is the low-income population. So this data is actually retrieved from our MPO in Utah. So Wasatch Front Regional Council, WFRC, is in charge of the Salt Lake City metropolitan area. And then they graciously provided us with the low-income data. So this low-income group is classified based on 2010 census for the income grouping. So basically any household, the population that are making less than $35,000 per year. And then the data is produced at the TAZ level. And then when we try to retrieve the PM 2.5 concentration, so the reason that we are doing that is because Salt Lake City is considered a non-attainment area for PM 2.5, and because of the very unique geographical region that we reside in, we have very bad inversion problem, especially during the winter. So this is why PM 2.5 concentration is our focus. So this data is actually retrieved from a company called Purple Air. So Purple Air is an air quality monitoring network that build all these laser particle counters. So these counters can actually provide the real-time measurement of different pollutants. So PM1, PM 2.5, PM10. So in Utah, there are about 400 different public sensors that are distributed across the state. So this figure basically shows the distribution of the sensors, sensor rating. So this is what we call AQI, the air quality index. So it's a composite index built upon PM1, PM 2.5, and PM10. So you can see that most of the sensors are actually pretty much concentrated in the Salt Lake City area. So it gives us a very decent coverage for the purpose of our study. So in this particular research, we retrieved this PM 2.5 concentration from all these sensors in the Salt Lake City area for about 2 weeks, and then we average that for each and every location. But the critical thing is it has to be interpolated or mapped out to the entire geographical region instead of using the standalone sensor location rating. So in our study, we actually used a very classical spatial interpolation method called kriging. So the interpolated value are actually modeled by the Gaussian process. So we applied that to create a smooth surface for the PM 2.5 concentration. So you can see that this graph that I'm showing here is the PM 2.5 concentration at the TAZ level based on the kriging interpolation. So the way that we use this data to come up with environmental equity is for each and every bus stop that a bus is traversing of, we create a catchment area on that stop. So this catchment area has a radius of 1 mile. And then we clip this with the PM 2.5 concentration with the low-income population, and then calculate the total sum of this particular indicator. So basically, it's the multiplication of the low-income population and PM 2.5, and then we sum it up for this catchment area. So for all this bus stop that a particular bus is actually traversing of, we're gonna sum up all this environmental equity for each and every stop. So this gives the total environmental equity that each bus is associated with. So as you can see on this slide, this actually shows the environmental equity value that we come up with, but it's a histogram for all the buses within the UTA's network. So the majority of the buses actually has an environmental equity value that is below 25,000 microgram per cubic meter. So this actually accounts for about 90% of the buses. So it's highly imbalanced and highly skilled. So with all this introduction about the indicators that we have developed and also the optimization model, we ran through all this optimization model scenario by scenario. So, but for each scenario, we give a budget for that scenario, and then we run through the optimization. So the optimization is having a target to maximize the environmental equity. So with that goal in mind, this particular optimization will give you, with the maximum environmental equity that's achieved, how many buses you're going to deploy, and where are the buses you're going to deploy, and what are the on-route and in-depot charging stations that you will need to deploy. So this trade-off curve that I'm showing here basically shows after running each and every scenario in terms of the budget, what is the optimum solution look like for by running through our optimization model. So you can see that if we were to replace all these electrical buses, all these buses within the UTA's network, so 334 buses for replacement, what is the total cost? So it will have $335 million that are needed, and then 46 on-route charging and 112 in-depot charging needed. Note that when we run this NITC project, some of the parameters that we use are also changed compared with our previous effort. So for this XC40 new flyer model, the on-route charging station actually is costing $1 million each. And then it can only charge 1 BEB at a time. And then this XC40 fleet is about 792,000 per bus. And then the in-depot charging will cost about $350,000 and can charge 3 BEBs at a time. So I want to go through couple of examples to show everybody how the results, what the results look like. So this is one example case where we set the budget at $25 million. So how the deployment plan will look like. So there will be 26 buses. Given this budget, 26 buses will be replaced with BEB, and then this figure on the right basically shows you the routes that these 26 buses will be serving. So they will be serving 11 different routes, and then the distance will range from about 7 miles each to about 20 miles each. Okay, so the daily mileage for these buses ranging from 161 miles to 263 miles. So for this particular scenario, we will need 2 on-route charging stations and then 9 in-depot charging stations. So the 2 on-route charging, one is located in the West Valley Central Station, the other one is located in the Mill Creek Station. So this makes sense because in Salt Lake, actually, West Valley is the area where people suffer the most in terms of air pollution based on our preliminary study. So probably a lot of vehicles that are serving along different routes crossing through that West Valley station will be chosen because of the environmental equity that they can bring. So another application, another example that I'm showing here is if the transit agency is to set the budget at $60 million, so what would the deployment plan look like? So this is how the deployment plan look like, as shown on the right side of this slide. So for $60 million, there will be 63 BEBs to be replaced. And then this figure again shows the routes that these BEBs will be serving. And for this scenario, 5 on-route charging stations will be needed. So there will be 2 built in the Mill Creek location again. And then there will be 1 built in the West Valley Central Station again, and then 1 built in the North Temple, which is the Salt Lake downtown area, and then another one in the Central Station. So these 63 BEBs will have a daily mileage about 62 miles all the way to 263 miles. So this last application is if the agency is to set the budget at $120 million. So for this particular scenario, the agency will be able to replace 122 buses with BEB. And then for this one, we will require about 14 different on-route charging stations as highlighted in this black star on this figure, and then 41 in-depot charging stations. So these 14 charging stations will be distributed across all these different bus terminals, again, West Valley Central, Mill Creek, North Temple, Salt Lake, and some other places. So the daily mileage of these buses actually ranging from 62 to 263 miles. So this is just kind of illustration of what the optimization model that we developed is capable of, and then how some of the results can be used by the transit agencies in guiding the BEB deployment. I want to use maybe 5 more minutes to show some of the visualization that we have developed. So for the purpose of this project, we actually built an executable program to let UTA, along with maybe other transit agencies, to use our optimization tool. So essentially, for the tool that we actually developed, we will ask UTA to input the shapefile to the bus stops, the shapefile to the routes, and then the UTA's run cut file. So for each scenario, you'll be able to specify the budget that you want to set. And then by running this EXE file, you will be able to get the optimization result for each particular scenario. We published this code on NITC's website, but we didn't actually share the EXE file. So the main reason is our optimization is actually using the Garubi optimizer. So Garubi is actually a commercial optimization solver for mixed integer programming problems like what we have for this particular research. So it's not really open source. So instead of sharing this EXE, which really rely on the Garubi optimizer, we actually just provided our open source code to the NITC project. But instead of running this optimization on your own, so one of the things we developed is actually this online platform. So if you go to this sample website that we developed, you'll be able to interactively explore the results that we have built for the UTA or Greater Salt Lake region. So I will go to this link and then show everybody what that looks like momentarily. Okay, so this is the website that we have developed to integrate our optimization results and also let people interactively explore different scenarios. So as you can see, the top part represents some of the visualization that we produced, and then the lower part basically give you a little bit background on what this project is about, what are the challenges, and some of the related work, and some of our optimization model that this result is built upon. So on the left side of this website, you can see that there are a couple of different items in this drop-down list. So the first item is actually this transit analysis zone within the entire metropolitan, Salt Lake metropolitan area. And then the next couple of tabs, including the pollution concentration for this area, basically color-coded. Low-income population, color-coded as well, aggregated by TAZ, household population, as well as the employment level. Okay. So basically what user can do is looking at this graph that I showed in the presentation earlier, for each particular budget limit, we actually ran through our optimization model and provide an optimum result. So you can click on the particular budget scenario, and then on this Google map, you will see the deployment plan based on our optimization. So this deployment plan basically show you exactly what I showed in the presentation, the routes that these buses will serve, and also the charging station. And then this TAZ figure on the left basically show you the number of TAZs that will be impacted or affected by this particular deployment. So if you click on another scenario, so you will see the routing for all these BEBs that will be serving the charging stations, along with the TAZs that will be affected. And then the very last scenario here is, sorry, it will take maybe 1 minute. Okay, is where you're gonna deploy or replace all the buses with BEB. So that will cost about $335 million. What that deployment plan look like, and then how some of the TAZs will be affected. Okay, so this is a workaround, I guess, to show how our optimization result can be visualized and then can be used or interacted with the audience to evaluate or perform some of the results analysis. So with that, let me shift back to my presentation. So with that, I think I kind of concluded my presentation. So this is just a brief conclusion based on all these findings that we have developed. So essentially, I think either model, either the cost-driven or the environmental equity-driven model, the transit agencies will be able to make these planning level decisions based on their short-term, mid-term, or even long-term strategic goals. And then, of course, in the future research, the model can be extended to incorporate several different additional goals other than the budget and environmental equity. For example, you can build in the robustness of the system, maybe even building the partial charging capability, so on and so forth. So this concludes my presentation, and I know I'm running a little bit over time, but I'd be happy to entertain any questions you guys may have. Thank you.
Thanks so much, Cathy. That was great. So yeah, we are short on time, but you can submit your questions. We'll either try and answer them right now, or we can follow up on them. So Cathy, we have a couple of questions. One is about the bus replacement prioritization, and whether it's triggered by identification of specific stop locations that experience high levels of emissions, or does it consider the entirety of the bus route and the air quality levels throughout the route?
Yeah, so that is considering the air quality level of the entire route. Yeah, so for each bus, the environmental equity that this bus is associated with is calculated by all the bus stops that this bus is passing through. Yeah.
Great. And there was a prior question. It seemed like so much of the research and focus is on the placement of the charging stations, and just sort of wondering, like, in practical, like in real life situations, how easy is it to manage the different buses and how much of a charge they might need? Or is it something where it is kind of messy still with, like, this bus has been here a little bit too long, this is too short?
Yeah, I think that's a question. So certainly with this massive deployment, there are tons of other things that I think transit agencies will need to consider. Not only about the cost for the charging station and the cost for the buses, but there are some other things as well. So one of the critical things that our UTA has been concerning about is really the charging capability and then how that will interfere with the power or grid system within the network. So this is something that we are considering about. So we are collaborating with a couple of electrical engineering professors in the region to figure out the plan, because Utah Transit Authority, UTA, has been very, I would say progressive in terms of pushing this electrified public transit system. So we want to build a great network that is robust enough to accommodate all this need, not only for the electrical bus, but we are also considering electrifying the commuter rail, and then of course the light rail will need a lot of power support as well. So how to accommodate all these different multimodal public transit needs is something that we're currently working on. But actually not only that, with all these shared mobility needs and also the booming of electrical vehicles, we are really trying to make our power system, our grid infrastructure robust enough to accommodate all this charging demand. Yeah.
Great, and I think that is some of the other questions are on that forward looking and like, yeah, so there's questions about, you know, the costs and engineering and the engineering and potential upgrade costs, and how, I guess, in addition to that, just how, where do you see this going from here, you know?
Yeah, so right now we have implemented 5 different electrical buses within the region. So it's currently they are currently in operation, and we are constantly getting this daily operation data from them. So one of the things we are interested in is people have been saying electrical bus is low maintenance. But really, there are very few data that actually can support this particular conclusion. So we are currently in the process of evaluating the cost in terms of both maintenance, operating costs, and also some of the robustness and reliability of the system compared with the CNG bus fleet. And then one other thing that we have observed from the operational data is that oftentimes the bus gets charged even when there are still battery inside. So there could be range anxiety for some of the drivers. So there is certainly some kind of coordination in terms of how all these factors will be placed in when we do the strategic deployment. So for example, if we allow partial charging, so how would the partial charging will be happening during the day, and then why would that be happening? So all these different factors are all we are considering in the next step in terms of the strategic deployment.
And recently, when we were collecting the sort of outcomes of this research project, we had a quote from Hale Johnson from UTA, and he basically talked about how you're helping with the decision-making process. Can you talk maybe a little bit about how you've worked with UTA and the individuals there, and maybe the different roles, in sort of a way that maybe another transit agency could work with you or work with someone else who is interested in this?
Yeah, absolutely. Actually, so the presentation that I'm giving today is really using UTA as an example. But as I mentioned at the very beginning, this is really, we really appreciate NITC's support on this, because this is a multi-institutional effort across different campuses. So we are really hoping that this optimization model that we developed can be used by different agencies and further evaluate the feasibility of this model for different agencies. So my collaborator, Aaron Galoob, he actually implemented this for the TriMet network. I didn't present it for this particular webinar, but we actually have all these results published in the NITC's final report. So if any of the audience are interested in, feel free to take a look at the final report and see how the results look like. Yeah.
Great.
And yeah, of course, we always welcome collaboration with all kinds of agencies.
Nice, great. So we should wrap up soon. Is there anything that you'd like to add?
Yeah, so I saw that there is one question, Brandon, that I probably did not answer at the very beginning for this one. So there is a question from Patrick, I think. So I would like to use maybe 30 seconds to address that, if that's okay. Yeah, so
Great.
Patrick asked, does the calculation of the number of buses that an en-route charging station can serve consider the amount needed to charge each bus? Yes, that is considered. So we assume that each bus will, it will take each bus about 10 minutes to get charged fully. Before the cumulative mileage is set to 0. So if within that any 10-minute window, if there's any bus arriving at this particular location, we will make sure that the number of en-route charging stations are sufficient to accommodate all this charging need. Yeah.
Great. All right. So thank you so much, Cathy. I'd like to encourage everyone to join our next NITC webinar in July. Hopefully, Cathy, we have you on again soon with some more of your NITC research.
Sure.
Great.
Yeah.
All right. Bye.
Thank you, everybody.